Right, this is Concept Z. It's the honors version of our last concept, which is Dalton's law and Graham's law. So first, focusing on Dalton's law, if a mixture of several gases is placed in one container, each individual gas is going to exert what we call a partial pressure. This partial pressure of each is the pressure it would exert if it were alone. So if we have a mixture of, let's say, hydrogen and helium gases, and they have a total pressure of 2.1 moles of gas, that's their combined pressure. So if we were to take out the hydrogen gas by itself, and we got 0.6, and then helium by itself, 1.5. Again, those add up to 2.1. So we have a very simple, straightforward formula for this, is that the total pressure exerted by the mixture of gases is the sum of its partial pressures. So gas A plus gas B plus gas C, and so on, is going to equal our total pressure. So here we have a 20-liter container that holds a mixture of neon, argon, and krypton with a total pressure of 720 torr. If the pressure of the neon alone is 240 torr and that of the krypton is 410, what's the partial pressure? So we simply just plug in our values that were given. Our missing value is the pressure of argon, and by adding and subtracting, we get our partial pressure of 70 torr. So pretty simple. Now this is a little bit different. Here we're involving volumes. This is where the honors piece comes in. We have a container with a mixture of 300 milliliters of oxygen and 200 milliliters of neon. The total pressure exerted by the gases is 1,250 torr. What is the partial pressure of oxygen? So there's a couple of pieces of information we have to abstract from this. First off, let me pull each of these up. We're given the volume of oxygen, the volume of neon. I'm adding those up to get a total volume. Okay, we have the pressure of our total, which is 1,250 torr, but we're missing the pressure of oxygen. So in this case, because we're involving volumes and pressures, we're going to set up a ratio. So we're going to say that the volume of oxygen over the volume of the total is going to be equal to the pressure of oxygen over the pressure of the total. Okay, so we're going to go ahead and fill in the values that were given. 300, which is the volume of oxygen, over the total volume, which is 500, is equal to our missing pressure of oxygen over the pressure of the total. So you can see the totals are on the bottom, oxygen's variables are on the top. And then by cross multiplying and dividing, we get our answer, which is 750 torr. And we can go ahead and then calculate the pressure of neon from there. Okay. We can also use this if we're discussing moles instead of volume, and we'll do some of those in class. Now, one thing I want to talk about, and this is actually something that's going to be involving your honors reference table, so we'll talk about that more tomorrow in class. When a gas is collected over water, as is often actually done in lab experiments, there's actually two gases present in the container. The gas that we were interested in collecting and the water vapor. And this presents a little bit extra step that we need to consider. So when a gas is collected over water, again, we have two gases involved. So according to Dalton, this is the equation that we would then use, that our pressure over total is equal to the pressure of that gas collected plus the water vapor pressure. The pressure of the gas is found by subtracting that water vapor pressure from the total pressure of gas in the container. Again, our packet is going to have that vapor pressure of water at various temperatures given in kilopascals. So this is what it's going to look like in your honors reference table. I just told you it was in kilopascals, but actually in this one it's in torr and millimeters of mercury. Those are equal to each other in terms of units. So you may have to do a conversion or two and that type of thing. So here what we would do is look at the temperature of the water, and that will give us the vapor pressure of water. Okay, and we will go back to that in class tomorrow. It's pretty easy, just a little extra looking up. So moving on to Graham's law of effusion. Graham's law deals with the effusion of gases. Now, be very careful. Last year in biology you learned a lot about diffusion, and that talks about how they'll move from a higher concentration to a lower concentration. Effusion is a little bit differently. It's about moving through either a certain pathway or a porous opening, such as a pinhole. The principle of effusion depends upon the movement of gases, but it relates to the rate or speed of a gas as it goes through a predefined pathway, and how that rate depends on the molecular masses of the gas. So at a given temperature and pressure, we find that the higher the density of the gas, the slower the gas is going to effuse. That also means then that the greater of the molar masses of a gas or the greater the molecular masses of a gas, the slower it's going to effuse. Density is a little bit hard to use with a gas because it changes so vastly with temperature and pressure changes. So we like to usually look at this with our molar masses. So the greater the molar mass, the slower it's going to be able to effuse through that barrier. So we first could just have a simple multiple choice question: which gas would diffuse or effuse most rapidly? If we're talking about it diffusing most rapidly, then we're going to be looking for the one with the smallest molecular mass, which in this case would be gas A. Now there are some calculations at the honors level that I expect you to complete, and that involves this calculation. Graham's law states that the rates of effusion of two gases are inversely proportional to the square roots of their molar masses at the same temperature and pressure. So the rate of effusion of gas 1 over the rate of effusion of gas 2 is equal to the square root of the molar mass of gas 2 over the molar mass of gas 1. So you can see how those are kind of diagonal from each other, which is important in terms of you setting this up. So let's look at a couple of calculations to see how this is going to work. So here's the first question. Under the same conditions of temperature and pressure, how many times faster will hydrogen effuse compared to carbon dioxide gas? So we have rate of hydrogen over rate of carbon dioxide, making sure hydrogen is diatomic. Okay, that's equal to the square root of the molar mass of carbon dioxide over the molar mass of hydrogen. So we're going to fill in our molar masses using their formulas. 44 grams per mole is carbon dioxide, and 2 grams per mole is our mass of hydrogen. Then, doing the division and taking the square root, we get 4.969. This means then that hydrogen will effuse 4.69 times faster. Okay, so now we're actually going to use this information in question number 2. If carbon dioxide takes 32 seconds to effuse, how long will the hydrogen take? Well, we know that hydrogen takes 4.69 times longer. So 32 seconds divided by 4.69 gives us, 4.69 times faster, which means that by dividing that, we get 6.8 seconds for hydrogen. So again, a simple little calculation. We'll go over this a little bit more tomorrow in class as well and try out some more problems. Number 3, we have an unknown gas that diffuses 0.25 times as fast as helium. What's the molecular mass of the unknown gas? So we're going to use our equation, but what I'm going to first do is that rate of x over rate of HE is going to be equal to 0.25. You could think of this as 1 over 4 is kind of how I would tend to set this up. Then I'm going to set that equal to the square root of helium over our missing molecular mass. And then what you'd have to do mathematically is square each side to get rid of the square root, and then by cross multiplying and dividing, we get our final answer of 64 grams per mole. And I'll go over the math with some of you guys that might have a little bit of trouble in terms of solving for x. But I want to move this video along because we're almost done. All right, so 64 grams per mole is our missing mass, and we could go ahead and plug that back in and check our work to make sure we get that 0.25. And then that means that we are all set. So we'll go over Dalton's Graham's law again tomorrow quite a bit and make sure you feel comfortable with each of those.